we just repeat what we did in the last lecture. So we had these function spaces. We had this guy here, the probability measure on the function space. And the background here, the underlying point was that there is some PDE out there. And what we're looking for is the solution operator of this PDE. So, right. So for instance, you could think of minus divergence of a gradient of U equals to F. And the solution operator could be, for instance, G, which is a mapping from A to U. Okay, so this is what the solution operator here signifies. It's a mapping between two function spaces. And this is what we wanted to study. But the difficulty, of course, was what we have learned so far is that neural networks or other machine learning frameworks, they're just mappings between finite dimensional spaces and finite dimensional spaces. So they essentially approximate functions, whereas the task at hand is to approximate operators. And this is where the difficulty was. So as I said in the last lecture, what we do to solve this problem is to cheat to begin with. We will not cheat later today because we can't, but to cheat. And instead of that, make this big assumption that even though we have an infinite dimension problem, under the hood, we actually have a finite dimensional problem, because then we said, okay, so instead of having infinite dimensions, we are saying that this measure here, this is only supported in finite dimensions. So in other words, we reduced sort of an operator level problem to a parameterized PDE. And this was the sort of setup that we are operating in, right? So if you remember, the PDE here was the compressible Euler equations. I'm not going to write. Okay, so now the mapping here is from the shape to the flow, right? And this is what I showed you, that we could do this with some tricks on numerical analysis, in particular by training on low discrepancy sequences. So this was a part of the lecture last time, training with low discrepancy sequences. We can learn this map. So for instance, we can approximate the fields or the observables with deep neural networks. So by cheating, we could achieve some solution to this problem to some extent. So what I want to do now is to give you a very, very quick sort of an intro or description of sort of a downstream task. So let's consider a downstream task. So last time I had a downstream task, which is uncertainty quantification. I was rushing through it a bit. So today I'm going to do a downstream task, because at the end of the day, you don't solve PDEs just for the heck of solving PDEs. I do that because it's fun, but most people don't do that. They solve PDEs because there is some output. You want to do uncertainty quantification, you want to do design, you want to do inversion, things like that, right? So let me give you a little bit of detail on one of them. So we still have the same assumption here, which is that we have a finite dimensional problem. Okay, even though you could write it at infinite dimensions, on the hood, it is a finite dimensional problem. Okay, and this application comes from what is called PDE constraint optimization. And it's a very, very broad topic. I mean, the standard textbook of it is this thick. It's like thousands of pages thick. But let me give you an example in 15 minutes, which is also quite interesting. And this comes from the shape optimization for airfoils, the same problem that I've been saying repeatedly again and again, that it's important, right? So as I said, at the end of the day, we want to optimize the shape in order to, first of all, let's try to do it in a step-by-step manner. So first thing is that since we are in this setting where I have to parameterize things, right? So what we do is we are going to parameterize them by some basis functions. So these are what are called Higgs-Henne basis functions. These are essentially splines. So those who know what splines are, they know what it is. But at the end of the day, I'm going to parameterize this entire shape, not as a function. I could have done that, right? I could have taken a level set function and I could have parameterized it. Instead of that, what I do is I just write it in terms of splines. And this number d bar is anywhere between 20 to 50. Okay, so this is sort of the constraint that we have. And the idea is, so this generates shapes. For instance, here is the base shape, so usually in aerodynamics or in any subject, I don't take my iPhone and then say, take this as my base shape and try to optimize it for a flow, because this will lead to thousands of iterations or hundreds of thousands of iterations probably, right? You start with something which is looking reasonable, and in aerodynamics, it's always teardrop shapes, because these, as we know, are sort of streamlined. So this is a shape which is what is called a base shape, the one that I'm just drawing now. Okay, so now the idea is that, so you have all these possible shapes, so you perturb these shapes and you are inside this design envelope. And then you don't want the shape that is at the margin, right? This is not going to give you a good flow. This will be too flat and too non-streamlined. So the idea is that we are going to change the shape of the airfoil so that we are going to minimize some flow parameters. And there are two important flow parameters, the lift and the drag, right? And usually people play with these two parameters. So as you know, probably even from high school, or at least very, very basic physics, what you want is the lift to be as large as you want and drag to be as small as you want, right? Because the lift is what keeps things up to some extent and lets it fly, and the drag is what pulls it back, roughly speaking. So people either fix the lift, say that you need this much of lift, and then you try to minimize drag, or they change what is called the lift to drag ratio. So these are the two options that you could do. But remember, so how is the mathematical problem then? So the mathematical problem takes the following shape. So at the end of the day, we have the compressible Euler or Navier-Stokes equations. Navier-Stokes equations. So these are the PDEs which govern the flow of a fluid around a gas, around, or air in this particular case, around the airfoil. And we want to find a shape. So now shape is not given in terms of a function. It's simply given in terms of these parameters. And these parameters, as I said, are anywhere between 20 to 50 dimensions, roughly speaking. So we are going to find a shape that is going to minimize a certain cost function or loss function, right? And what is the loss function? As I said, I want to minimize the drag. So this CD is nothing but the drag. It has a simple formula. I'm not going to write down the formula, but it's some drag. And the CD is a function of y, but it's also a function of the PDE solution, right? Because after all, you have fixed the shape, you have the flow, which is defined by the Euler and Navier-Stokes equations. You compute the body forces, the pressure, and you take the difference of pressure and you compute the drag. So that's the first component. So this is the drag coefficient. Some people also call it as the drag coefficient. Then you have, you remember that I wanted to keep the lift constant, right? So this is modeled by this term here, which says that I have some reference lift, which is, for instance, computed at the base shape. And then I keep any perturbations of the lift penalized. Okay, this number could be something like 1,000, roughly speaking. And then these are some design constraints. So these are what are called design constraints. So you don't want an airfoil which becomes so thin that it cannot be manufactured. So you need some structural stability, some design constraints, and these are sort of modeled here. So this is like any optimization problem. In any optimization problem, you have an objective function and you have some constraints, and you can think of these constraints either penalizing them or using the Lagrange multiplier, something like that. And how do we do it with the classical optimization-based algorithm? Okay, so what you do is just use gradient descent, because this is what we can also use non-gradient descent-based methods, genetic algorithms, particle swarm optimization, but these are not that common. So what you do is gradient descent. What is gradient descent? Y L plus 1 equal to YL minus some learning rate of the gradient of Y, J of YL. So this is what gradient descent is, right? We also do this in machine learning, but also in traditional optimization. So at any iteration L, so L is the Lth iterate. So at this iteration, you compute the gradient with respect to this iterate, and then you march in the direction of the gradient descent. You descend in the direction of the negative gradient, right? So what is the issue then? The issue is that not only do you have to compute the state, so at each iteration, you have to compute the state, which is given by YL. Remember that this is the shape, but you have to also compute the loss function, right? So loss function would mean that I have to compute the drag, I have to compute the lift, and I probably have to compute the structural constraints. So this is structure. So I have to do these computations, and each time that means solving a Navier-Stokes equation, which is very, very time consuming. So how do we do that? How do we compute these gradients? It's not so easy. You could do finite differences, but no one does that. Instead, you have to do what is called an adjoint solver. Means people who have done some optimization know this, that you can use something called the Pontryagin maximum principle and write everything in terms of an adjoint. It's very complicated to solve. And okay, so let's resume. So you have to, and this is expensive, right? So remember that I have to do this optimization, and that requires multiple. Let's say that I take 500 iterations. Now, each iteration, remember from the last lecture, this takes for the direct problem, it's approximately 3 or 4 minutes or whatever, 5 minutes. So if you do 500, that's already a very long time. But at the same time, you have to compute what is called adjoint, right? And this adjoint is at least 3 times more expensive than the direct problems. So the computational cost is humongous. And this is a good reason why companies like Boeing, they have their computing budget is in the billions. Every year they spend more than $2 billion just on their computing costs. So it is, in fact, unfeasible in certain cases. Not only is it complicated, but it is unfeasible, particularly in 3D, because you can imagine how the costs are going to scale. So what does one do in that case? Of course, you know what we're doing in this course. We can use a machine learning solution so that this would be a perfect downstream task for that. Okay, so how do we do that? So the straightforward way, and this is what I have written here, is like a surrogate optimization algorithm, is very simple. So what you do is that you choose a training set. Remember that now everything is parameterized. I'm only operating within the parameter space. So at best, I'll get shapes that are going to be parameterized by these parameters. I'll not get any novel shapes in this, but I will just operate within these constraints, right? So then what do? I take a training set, whatever random low discrepancy sequence, so-called whatever we have learned that low discrepancy sequence is better. So we can do that. And then I'm just going to train a neural network, which takes the shape as the input. Why? This is the shape parameters. And as the output, I will output the drag and the lift. This is what I also showed you last time. So I can do this. And now all that I do my training up front. Let's take 128 samples, do the training, have a surrogate, which is going to compute the lift and the drag. But remember that this one was very, very fast, right? This was like a microsecond or 10 microseconds. And then if you do that, then all that I do is that, and also because these are neural networks, they're completely differentiable, I can just replace everything by the neural network. So just replace the drag and the lift with the neural net, the ones computed with the neural network, and I can compute whatever I want. The gradients, because it is completely differentiable, right? So neural networks are differentiable, Hessians, second derivatives, whatever. And this is backpropagation, which is great. And then you run the optimization algorithm. Typically, people use what is called LBFGS. You have already seen that in the lectures on pins, that this is a very powerful algorithm. So this is a plain vanilla algorithm. You take data, so 100 simulations, you train it, and then you let it run. You have the neural networks where you replace them, and then this algorithm will run within a second. Right? Once the training is done, the training is expensive in some sense because the data generation is expensive. But once it is done, this is going to be cheap, right? So it's such a straightforward algorithm. And given the sort of results we saw last time, it should do a good job, right? But of course, there's always a catch. You can do that, but there is an issue here. And the issue is very simple because remember that just imagine this to be your parameter space. So this is your capital Y. This is a 20-dimensional object. So now you have the parameter space. And remember that how do I choose my training points? I wanted equidistribution, right? So equidistribution simply means that I have my training points all over. However, this is the catch, right? Because a minima is not, because minima doesn't lie. First of all, there could be one minimum, then you are anyway screwed if it's a convex function, because it's just one point. But more than that, minima are usually submanifolds. So the set of minima could be something like this. I don't know. I'm just drawing a curve like this. You'll see some examples later on in a minute. So what does it mean? It means that the fact that I have uniform distribution, unless until I have a lot of data points, this is not going to hit the minima, right? So remember, the minima is a small set within this is what we want to approximate. Instead, what we have is some sort of a global approximation. We are taking data from everywhere. So of course, training points are not going to represent the minima well. And this is what is represented in this picture here. where we do the lift to drag ratio. Means we're keeping the lift fixed, so we're just changing the drag. So now you can see what we are interested is in high lift to drag ratio. Remember that, and this is where we are, right? So let me draw a picture here. So this is the area where we want to represent. But when I just take 64 samples, which is a reasonable number of training distributions, I don't represent it at all, right? So all the training points that I'm choosing are going to be far away from my minima. They're all concentrated around a region which I'm not interested in. Because if you choose a random point or a snowball point, they will hit somewhere here. What you're interested is in hitting here, right? So this is the reason why if you use this algorithm, it will either not reach the desired minima because your neural network has not seen that area where it is what is interesting to us, or it could have very large variance in the sense that sometimes it might hit the minima and sometimes it might go somewhere else. Okay, so did you understand? So the bottom line is that we have an algorithm that has been trained to approximate the neural network, to approximate the underlying function all over the parameter domain. On the other hand, minimum is a sub-manifold of the parameter domain. So unless until you have lots and lots of points, you're not going to represent this sub-manifold well, and because of that, there will be issues. Okay, so just using a plain vanilla neural network doesn't make any sense unless until you have lots and lots of data points. But if I have lots and lots of data points, why on earth should I train my network? I can as well do my full optimization because I will do so many number of iterations. So is the issue clear? So there are ways to overcome it. One is by doing lots of data points, which is unrealistic. Otherwise, there is a smart algorithm which can do it. And this is what I want to explain quickly, right? After having spent half the time in trying to fix how the screen behaves. So here is a toy model. This is no longer aerodynamics. Aerodynamics will come in a bit. And this is a very interesting model because it's I don't have anything, but you take some projectile, whatever, let's say this one, and you just throw it, right? So it's like a ball throwing example. You take a projectile and you just throw it. And what you're interested is in optimizing the range, right? So you want to take a ball and throw it as far as you want. And what are your control variables? They are your release velocity. How fast do I throw it, or do I throw it slowly? Or and your release angle. Means, of course, if I throw it like this, it will go very different distance than if I throw it like this, or if I throw it like this, right? So this is a very simple toy model. It's just ODEs now. It's no longer PDEs, but it tells you the story quite well. So what is the, briefly, what is the problem here? So we want to minimize the, so what is the dynamics? So dynamics is essentially Newton's laws, right? So dynamics is that you have dx by dt is equal to v. So x is your coordinates. So let's say that we are in 2D because the 3D is not necessary. We're in 2D, for instance. It could be 3D. It doesn't matter. And then dv by dt. So this is the acceleration, which is the force, which is essentially the drag force, which depends on v minus gravity. Okay. Now, those who know aerodynamics know a formula for this drag force. I'm not going to write the formula; it's cumbersome. But so these are the equations that model this. And now your so your initial point. So you have x naught is given by some r cos alpha, r sin alpha, and your control parameters are precisely these. Okay, so these are the code, or v cos alpha and v sin alpha. So this is the release velocity, and it's the release angle. So this is v and this is alpha, and you have to maximize the range. So this is the horizontal range. You can write down an expression for it. I don't want to bother writing down the expression. And then you keep on throwing balls, and these are the different trajectories, and this is sort of the spread here. Okay, you don't have arbitrary angles to throw, and depending on how the wind is and what is the density and so on, the drag force tells you what is your release angle and what is your release velocity. So it turns out that in this case, because it's a constraint optimization problem, you have a set of maxima, and this set of maxima, they lie along this curve here. So you see this curve? This is what I was referring to. So any of these points is going to be a maximum. Okay, so this is you can actually solve it. If the drag is linear, which it isn't, I could have solved it by hand, but numerically you can determine that this is where it is going to lie. But now you can imagine that if I train my neural network, I will train based on, so these are probably sample points. These are Sobol points, probably. I don't remember now, could be random. I think they look like Sobol. So these are Sobol points, and you can see that they're not too many around this minimum. So there could be issues, right? So the idea would be to somehow take into account the fact that we have an optimizer which is going to live in this submanifold and somehow choose training points along the submanifold. Or in other words, the bottom line, or the aim at least, is choose training points near the extrema. And there is an algorithm which can, there are many algorithms which can do that, but there's an algorithm which was designed in my lab a couple of years ago, which does it quite well. It's called ISMO. It's called Iterative Surrogate Model Optimization. And I just want to graphically tell you how it works. Okay. It's a very simple algorithm. Anyone can code it up very quickly. So the idea is that now remember that we have a computational constraint. We can't have 100,000 data points, because if you had 100,000 data points, anyway, this manifold would have been represented rather well, right? So there would have been no issue. The training would have worked, and you could have done the optimization, and it would have worked rather well. You don't have that freedom. So instead, you have, let's say, 128 data points. It's a maximum that you can consider. So what it does is that it chooses the training points iteratively. So let's say that at each iteration, you have 16 training points. These are 16 training points. And this, it starts with, let's say, Sobol points, or probably random points. I don't remember now which one. Doesn't make a difference, right? And this has nothing to do with the extrema. Remember that the extrema is represented here. So it has nothing to do with the extrema. So what do we do in that case? We just train the neural network and solve the optimization problem. This will probably not give you a very accurate result because it's only 16 points. But we are not going to use that. So what we are going to do now, okay, in this case, because it's a very simple problem, one iteration is enough. So what you do is that these new points, so train your neural network, train NN, and solve optimization problem. And then use optimizers. This is, of course, approximately, right? Because it's a very bad situation. And use optimizers as training points in the next iteration. As training points. So in other words, you started, and keep your old points, means you can as well have them. So the next set of points, you just take the optimizers from this imperfect neural network, and then you get this structure, a little bit of the structure here. In this particular case, you're lucky in one iteration, you can get it, and you repeat it. So you train, optimize, and use the new optimization points as your new training points. Train, optimize, put the optimization points as your new training points, train, optimize, and so on. Okay, so it uses the power of iterations, and in fact, in the proofs, one uses sort of a geometric convergence. But just graphically, this is what happens. This is after second iteration. So we have 48 points now, and you can see that they are sort of filling up here more and more. The neural network is getting more accurate. There are, of course, some points which have nothing to do, so some points which are falling off. But now you can see in 4 iterations, it starts really hitting this curve quite well. So it's an iterative process. So you train, optimize, use the new training points as your optimizes as your new training points, repeat the process. Okay, there is a description of the algorithm. You can look it up in the paper, or you can look it up in my notes when you get it. But the idea was essentially you keep on doing this iteration, and then you can prove in some simple cases that this will converge exponentially fast, whereas your traditional algorithm will only converge algebraically, but only if you have a convex problem. In a non-convex problem, it works quite well. So here's an example. As you can see, maybe I explained this. This is this horizontal range optimization. And now the baseline now is my plain vanilla algorithm, which is a deep neural network, which has been trained on equidistributed points. And you can see that very quickly. So let us look at somewhere around here. So eventually, of course, there's a lot of variance in the original problem, right? So more number of iterations, it still keeps on having a variance. But here, very quickly, within 1 or 2 iterations, you hit the minimizer, okay? So with very, very few points, you could accurately represent the optimizer. Is that clear? So this is a very, very simple problem. But let me show you what are the results for the airfoil one, right? So here are the results, and these are very interesting. So let us look at the baseline. So baseline is I replace my numerical method, Navier-Stokes solver or Euler solver, with my DNN, right? So this is what is called DNN opt. I should use another color, red. And then you can see that as a function of iterations. So in the uniform case, what I do is I just keep on adding uniformly these points, right? So that there is a fair comparison. And you can see that the basic issue is that the variance is too high. Even the mean is very difficult to discern here, but the variance is too high. The drag does go down, it eventually does go down, but with too high variance. So it's essentially useless. It relies on luck. But with the method that I just suggested, where you train and use your optimization points as your training points, you can see very quickly, not only does the mean decay, but more importantly, the variance, there is some variance, right? There is some uncertainty in this problem, so there is some natural variance. But more importantly, very quickly, the variance decays considerably. So variance is significantly less than what it would be for just using a plain vanilla neural network. So this works. And what is more important is that, okay, just quickly, so the airfoils that you obtain, they do the job. Maybe perhaps you can see it better here. And this is why this is an interesting problem, right? So the drag is reduced by 50%. Well, if you could do that for a real aircraft, that would be phenomenal, right? But you don't have that because real aircraft are in 3D, the physics is more complicated. So there, a reduction of drag by 5% is like several billion profit for the airline companies. So you don't do that. But in an academic test case, you really reduce the drag. And there's a reason for that. I'll tell you in a minute. So the reference drag was 115 units, whatever units they called, and this one is 58 units, the optimized drag. So it reduced by almost 50%. But the mean remained the same. In fact, the lift remained the same. It just went up a little bit. Okay. And you can see the point is that the base shape, which was in the dashed lines here, okay, you can see that there are these minor changes, right? So these are two optimizers. These are these minor changes here. We could never design it by using some heuristics because there's no way you can design it. You need some algorithm to do it. And just by making these tiny changes, you can get a drag reduced by 50%. And the reason why this happens is, okay, so I'll say that, perhaps I say that in a minute, is because this is the actual flow that has been computed. So you can see most of the drag here is what is called a shock drag. There was a big drag shock here. And then by changing, you essentially weaken the shock. So you can see that the shock becomes weaker. Also here, the shock becomes weaker. And this is why the drag gets reduced. So this makes a lot of sense, physical sense. But this is the real sort of test, which is how much better did you do in comparison to the, let's say, the best state of the art. And the state of the art is this algorithm here, which is based on, at each iteration, you call the numerical solver. Okay. And these are the number of solvers, the number of times you call the solver from the simulator. And let's say that we want to reach, let's say, this level here. And then this is where the comparison is. So this takes me 2048 calls to the forward solve, right? Here, this takes me, I don't know, 80. So this is the difference between them. Because training the neural network is trivial, inferring the neural network is trivial, all the costs are in the data generation. And the data generation is done with respect to this expensive aerodynamic solver. And you can see that this is 2048, but with this new algorithm, you can do the same with just 80 calls to the solver, right? So 80 and 2048, that's factor of 30, which is which is what it is, right? So that's a considerable amount of saving. So this is the whole point of doing anything with the machine learning, is to do this kind of downstream tasks faster. So in this particular case, I showed you an example where the downstream tasks can be done faster, but if you just use a plain, yes, go ahead. Yeah. This could be a little bit, but this could just be some precision issues or something like that. Means no one will run this algorithm up to here, so in practice it is never run. So it's sort of I don't think it will go down any further, because this is already quite a lot. How 4096 solves are quite a lot. Usually people don't do more than 1,000. So I don't think this is more numerical noise. So roughly, yeah. So this is the whole point, right? Roughly, it could achieve the same. It of course saturated at some point, because machine learning is at the end of the day, there are some, you can't take the error below 1%, right? So roughly speaking, 1% is the limit. And with this algorithm, it's nothing special about my algorithm. It's a very simple. The point is, the 2 points here, right? First, it works by using a machine learning surrogate. However, it does not work in a plain vanilla manner, where you can just replace things with a neural network. You have to pay attention to what you're doing, right? So this was sort of the main message. So, but these are sort of the downstream tasks that we could potentially handle with machine learning. Okay, so let me stop here and take the break. After the break, what I want to do is all of this work, and there are many other examples like this from my lab and from other labs. The idea is that you have this, where is the assumption now? This assumption, right? And this is what, okay, in this particular case, it worked because some people have worked for 50 years to provide you with a good parameterization. So this Hexana parameterization has been around from the 1970s. So this is a lot of expert knowledge, right? And in many, many cases, you don't have access to that. Particularly with new applications, you will never have access to these kind of parameterizations. So after the break, I will try to explain to you why this is such a big limitation and what needs to be done when we remove this kind of an assumption. So we can't cheat. We can only cheat up to a point. But after that, you really have to stop cheating and really solve the operator learning task yourself. Okay, so let's take a break. Today, let's make it a bit shorter. Shall we say 10 minutes? So we are all here at 10 past. Okay. Then I pause the recording. Okay, so let's begin. So what are the issues with this big assumption that we made? So remember, what was the point? So we had the operator G from X to Y. And this is sort of the PDE solution operator. And we had that the dimension of the support of the measure, mu, was finite. Some ty, which is finite. And mu was the probability measure on functions, right? So what is the issue with these parameterizations? First of all, as I said, it's very difficult to come up with a suitable one. It takes expert knowledge, expert domain knowledge, right? So for instance, for the aerodynamics examples, the ones that we just looked at, so there's a lot of expert knowledge. There are, in fact, at the moment, there are exactly 2 parameterizations. And you can imagine how many aircraft are manufactured, how many companies do it, and yet there are only 2 parameterizations. So it takes quite a bit of time to build up that expert knowledge. So when you have new fields or new problems that need to be solved, it is sort of intuitive to think that it is difficult to come up with a suitable parameterization. So it's difficult. So if you want to work with shapes, it's much easier given a shape. It's much easier to say what is the level set of the shape, right? This is a mapping that one can come up with. But now find a suitable parameterization for the shape. This is far from trivial. The second thing with parameterizations, which is these 2 things are sort of related to each other, is that they're far from unique. It means you can have different parameterizations doing the same thing. So let me give you an example of it, right? So let us say that you have just a mapping 0 to 1, and you have a mapping f of x equal to x squared. Okay. And the task is to learn this mapping, but I could reparameterize it very easily in the following manner. So I'd say A1 is x, Y2 is A2 of x plus B2. And now my function f, capital F of Y1, Y2, I would simply call this as half of Y1 minus B1 by A1 squared plus half of Y2 minus B2 by A2 squared. So as you can see, it is exactly the same function that is being learned, right? So the function that I'm asking is just f of x equal to f of x equals to x squared, but I'm rewriting it in terms of a slightly different parameterization like this. So now what is the issue? Why is this an issue? So let's say that you are trying to learn, you have trained a neural network that when given a number is giving you its square, right? And now everything completely stops, that instead of having one number, I'm giving you two numbers which actually represent the same number, and I'm asking you to compute the square, because your neural network only knows how to take one number and take it into another number. It has no clue about how to take two numbers and produce one number out of it, even though they are exactly the same objects. So this is a heuristic way of saying that parameterizations are far from unique, and learning a parameterization only means learning a parameterization. You're not learning the underlying object. So now you can see that instead of just doing it twice, I can do it infinitely many times, right? I can just jiggle it around or juggle it around, and I can get a completely different answer. And this is primarily the reason why there is no generalized or it doesn't generalize well, maybe is the statement. What do I mean by that? So let's go back to this example, right, of the aerodynamic shapes. Let's take this. In practice, if you go in the aircraft and you look at the wing, the next time you look at the wing, you will see that the wing is not exactly in one piece, but it is best represented by sort of three pieces. So this is what is called a multi-component airfoil. And this is done for reducing drag and so on. So instead of that, there is a tiny piece here and another tiny piece here. I could have drawn them, right? And these pieces, they do matter. They do, but the same parameterization can no longer parameterize them anymore. Okay. So if there was a 20-dimensional parameterization that parameterized this shape, I need 4 to 6 numbers to parameterize these additions to the shapes, right? Now you have trained your neural network to take a 20-dimensional object, the shape, and to get out a number, let's say the lift. Now I perturb it slightly and I produce these airfoils here, these multi-component airfoils. Nothing can be done, because all that I need, all that I know is how to go from 20 dimensions and produce a number. And that's what I'm fixed. Any change in parameterization, for instance, introducing this multi-component airfoils, there's no chance of being able to approximate this. Is that clear? So this is sort of the basic issue. Or here's another example. Maybe if I have time, I will do more about it in a couple of lectures. I'm pretty sure I'll run out of time, so let's not overpromise. But let's try to do the following thought experiment. Okay, so you have a body, or you have some domain, and you have some. Let's say that this is some part of the ground, and you have some objects that you want to detect. Let's say that you have some objects that you want to detect. And the way you do is that you put in some sources here, you send in some waves, right? Send in some waves, and these waves, they reflect, some reflected waves are there, and these are sort of detected, for instance, on the boundaries somehow, right? So this is, you can model it by using the wave equation, you can model it by using the Helmholtz equation, and so on. There are different ways to model it. But now if I want to parameterize the problem, I remember that I'm looking for 3 objects that need to be detected. I can parameterize them, no problems. I could parameterize them. You could parameterize them by the location, which is in 2 dimensions, in this case, 6 numbers, location, and then possibly the radius. So that's 9 numbers, you can parameterize them. And you can train your neural network, it will probably give you a reasonable answer. But now if I spoof it a little bit, for instance, by introducing a fourth shape, a fourth square, then you're finished, right? Because whatever parameterization has parameterized 3 squares, 3 objects, cannot parameterize 4 objects anymore. It's exactly the same problem that I showed you with the airfoils. So the point that I'm trying to make is parameterizations are not only difficult to come up with, but they are very difficult to generalize, because whatever parameterizes one particular problem just parameterizes that problem. Is that clear? So the cheating is only up to a point. So it's okay, but you cannot go beyond that. It's very limiting. It's like a straitjacket. If you like to maneuver a little on the sides, you're finished. So you cannot work with parameterizations in general because of these reasons. So we have to genuinely solve the problem that we started out with. Clear? Okay, so we're back to operator learning. That is, we really have to learn this map. So G, which is a mapping from X to Y. This has to be learned. And remember that this is my input, which is a function. This is my output, which is another function. And we have to learn that. And we have to find a surrogate. So inputs and outputs are functions. You cannot just work with numbers. You have to work with inputs and outputs. And this is what we do for the remainder of this lecture and the next couple of lectures. We genuinely have to deal with functions. Okay, so the rationale for that is now quite clear. But now the first solution, probably you might have already thought about it, because when I said, for instance, here, I thought that one way to explain it would be if I would have some sort of an encoder which takes X and produces Y, then we could have generalized better. It's in the same sense here. So here's a solution. And let me try to spend some time on explaining what the solution is. Actually, it's solution number 2 because solution 1 was to cheat, but at least in this lecture, it's my first solution. So what is the problem that is being solved? The problem that is being solved are the Navier-Stokes equations. So you have Navier-Stokes. So in 2D, we can write them like this: ut plus ux plus vuy equals plus px equals to 0. Let me just write down the equations. Vt plus uvx plus vvy plus py equal to 0, and ux plus vy equal to 0. Oh, this is Navier-Stokes, sorry. So it can't be 0 on the right hand side. So I remove the 0 and add new uxx plus uyy, new vxx plus vyy. So what are these objects? Since we are going to deal with Navier-Stokes equations many times, so u and v are the x and y velocities, and p is the pressure. Okay, so now there are 3 variables and there are 3 equations. This is just in 2D. In 3D, the extension is quite straightforward. Okay, and this is the Navier-Stokes equations. This is the fundamental equations of fluid dynamics. It turns out that there is one more quantity, which is called a vorticity. Many of you might have seen what that is. Vorticity, which is omega. It's essentially the curl of the velocity. Curl of velocity. In 2 dimensions, it is what is called a rot, or it's Vx minus Uy. Okay, so this is the vorticity. It turns out that once you have the velocity field, you can always compute the vorticity, and it is sometimes useful to work with the vorticity instead. It turns out that so the task, the operator that I have here, G, is a mapping between some initial vorticity. So this is initial vorticity to some final vorticity. So this is at some later time t. Okay, so this is the operator. I've been given some initial vorticity, which looks like here, and then I want to map it to the final vorticity, which looks something which is relatively different. Okay, it's a very clear-cut problem. Given an initial vorticity, by the way, you could, from a vorticity, you can also get the velocity field in 2D. This is a unique mapping. It's called a projection or a Hodge projection. Anyway, so you've been given some initial vorticity and you take it to some final vorticity. So this is the operator that you are interested in learning, right? But remember that the input is a function. So in this case, it's an image, it's vorticity. So it is an image. Let's say that we have been given the fundamental domain 0, 1 squared. So this is my computational domain. For simplicity, it need not be like that. And then I just need to learn this mapping, right? So this is a function, vorticity, this is also a function. I can even tell you which function spaces they belong to, but that's not important for the lecture. So function to function. So how do I learn it? So of course, I can't just use a neural network to a function, right? Because neural networks, they take in inputs as vectors or tensors or whatever, arrays. You cannot lists or strings, sequences, you cannot work with functions. But this is the way I can do it, right? So what I'm going to do is, let me explain it a little bit carefully and take the time to do it, is that, okay, so I have been given my initial vorticity. It is given on 0, 1 squared. So I can always, given a function, I can always sample it on a grid, right? So these are some grid values. Okay, so here, so the sampling is on a grid. So given a function, I just read out its grid values. Okay, so in this particular case, you could, I don't remember how many elements are there, but it looks like 16. So it's a 16 by 16, very coarse mesh. But let's just, for the sake of argument, say that it is written on a grid. So instead of having a function, someone has a question, or instead of having a function, all that I do is that I sample my function at grid values. Okay, so I have rearranged it into a 16 by 16 array. Okay, it could be 64 by 64, 256 by 256, 1024 by 1024. You decide the resolution. Let us say we have access to a function, so I can sample the function at any point, right? This is the whole logic of having a function. So now, similarly, what I'm interested in the output. Okay, so the output, you can say that I want to know the function at any point in the domain, but in particular, if I knew it at a 16, it would be a very coarse representation of the output. But if I knew it on a 16 by 16 grid, I could do an interpolation, right? Because how do we, given point values, how do we recover functions? We do interpolation. So given a value at some points, I could do interpolation. So at the end of the day, if you think of it carefully, as long as I can take my function, project it to a finite dimensional space, for instance, values on a grid, process it at a finite dimensional level, and then I have again the values of the output on the grid, I can go back to functions, for instance, by using interpolation or some other way. Then I have somehow avoided the problem of dealing directly with functions to functions. Instead, I have function. Okay, I have functions. This is function to grid values. So this, you can reshape it as vectors for simplicity. And also here I have vectors. And then I can go back to function through interpolation. You got my point, right? So I start with a function, I sample it on a grid. And now I can reshape it as a vector. I can rewrite it as a tensor, whatever I want to like. I process it and I recover it also as a function on a grid or values on a grid, values of the output on the grid, and then I interpolate back to functions. Okay, so I have reduced my infinite dimensional approximation problem, my operator approximation problem, to something which is finite dimensions. All that I do is that on top of it, I have used a sampler, which is going to give me discrete values of the function, and I've used an interpolator, which is given a function, it is going to get back the interpolator. So this is sort of the rough idea. And in between this mapping, I could use a neural network, right? Because after all, neural networks, we know they are universal, right? So any function between a vector and a vector space and a vector space, I could approximate it by a neural network. I personally, in this particular case, if you don't want to just look at 16 by 16 grids, but if you want to look at, for instance, 64 by 64 grids, then this will be a mapping between a 4096 dimensional object, a 4096 dimensional object. And if I use a dense neural network, you can imagine how big this neural network is going to be, right? So I don't want to use such a dense neural network. There are other reasons why I should consider convolutions, but let's say that one way to sparsify this dense neural network is to use convolutions. But this is just one alibi or one alias here. You could use something else. So in between, I'm going to use a convolutional neural network. Ben has introduced convolutional neural networks in one of the lectures. And later on, maybe in a couple of lectures, I will reintroduce them. But this is just a way to sparsify. You could have used a dense neural network here. Dense, just to sparsify. So you see how is my processing happening? given a function, I read out the grid values, process them either through a convolutional neural network or a dense neural network, transformer, whatever you want. And then I get another set of values on a grid, interpolation back into function. So I process from functions to functions. So all this sort of elephant that I had put in front of you, this beast or operator learning, it turns out that I can do it in a very simple manner. I just take my function, evaluate it on grids, process it, and reinterpolate. Done. Right? So if this was that simple, I wouldn't be saying it, right? But it can be done. You all agree with me that this is a process that indeed can be done. And let's do it. Let's do it for maybe a slightly more difficult problem than this one, which is again with Navier-Stokes, but with very high Reynolds numbers. So essentially it's Euler equations. These are data that Tobias, who is sitting here, has generated. So this is let's say Navier-Stokes with zero viscosity. And now instead of the vorticity, well, it could also be with the vorticity, but we look at the velocity fields because then the results are what they are. Okay, so essentially I take a vorticity, which this is my input, and this is my output. You could also do that, but this is a very simple problem. I just wanted to explain the problem here. Or this is your input, and this is your output. And you repeat this process. You sample it on a grid, you sample it on a 64 squared grid clearly, and then you do this interpolation to be able to evaluate it anywhere, and you train it, right? And it turns out that it does a reasonable job. Means the error here, as you can see, is approximately 5%. Okay, 5% is not 1% like what we have seen here, but this, as you can see, is a fairly complicated flow. So it starts from these kind of shear layers, and it generates these vortices. So this is not the easiest thing that you can imagine can be approximated, but nevertheless, 5% is quite satisfactory. Why should I be unhappy with that? It turns out that there is a catch to it, and let me try it in this. This was identified by, among others, in this paper, but there are other papers where this is identified. And the idea is that in operator learning, it is not just about inputs and outputs of functions. It is something more to that. And what is that more? So let us go back to this picture here. Okay. Now let's say that I had a function and I sampled it on a particular grid, 64 by 64, and processed it. But since there is a function, nothing tells me that I should sample it on a 64 by 64 grid. What if I would have sampled it on a 128 by 128 grid? I can do that. I have access to my function, which means that I have access to all the values of the function. I can evaluate it anywhere, right? So this is possibilities available for me. Also, I could have sampled it on a 32 by 32 grid, and I could have evaluated it on a 32 by 32 grid. So if I've really learned the function and not just a particular realization on a 64 by 64 grid, then I should be able to handle input, which is sampled on 128 by 128 grid, provide a reasonable result, and sample an input, which is on a 32 by 32 grid, and provide it with a reasonable result. Otherwise, I have not learned the function. I've only learned a particular approximation, particular realization of it. And it turns out that you can do this kind of tests because you have access to the function. And let's do the test. So what is the test here? So the test that has been done here is that, for instance, on a 32 by 32 grid, so I sample the function, I run it with the same convolutional neural network, okay? Because the convolutional neural network has been trained, right? So I run it, and then I just evaluate the function on a 32 by 32 grid and interpolate to get the results. And this is what the error that I get. It is like 22% here. And I do it on the other direction. I do it on 128 by 128 square grid, and again get 22%. So not only are these very high errors, but more importantly, it seems to me that it has not learned the function at all. It has really learned the particular realization of the function on a 64 by 64 grid. Okay, because if it were, then it would be a relatively flat. Of course, nothing is completely flat, means there would be some machine precision issues, trainability issues, whatever, but it should be relatively flat. Instead, it's like the fluctuation, the deviation is like hundreds of percent, right? Four times, 5 times more. So it has not really learned the operator. It has simply learned a finite dimensional representation. So this solution is not a solution. It's as much of a cheating as the other solution, because now, since I have access to functions, I can evaluate them on grids, and then there has to be some resolution invariance, or let me write it, or equivariance if you want it. Let me call this here. So this is a very important point, and this is sort of the core of operator learning is this, to some extent, that at the end of the day, you need to learn functions and not finite representations of them for various reasons. I will talk about some of the reasons in the next lecture probably. One of the reasons is that my data could be available in multiple grids, right? So I might have some data on 32 squared, I might have some data on 64 squared, and I want to somehow operate, or I want to learn or train with both these data sets. And if I have this kind of a behavior, is a very subtle point. Even if you don't get it now, think about it. Ask me questions if you have any, that what does it mean to learn a function? It cannot mean that you learn just this, right? Because it has to be something more. And that something more is what sometimes, well, I call it as discrete continuous equivalence, which is that even though I'm learning things at a discrete level, it should still be equivalent, or it should in some way represent learning them at a continuous level. Or instead of just learning mappings between vectors and vectors, I'm really learning mappings between functions and functions. So that should be the aim. And clearly, a convolutional neural network used in this manner doesn't do this. Okay. Or in other words, it is inconsistent. So you can say that this is inconsistent. This is a loose way of saying it in function space. Actually, I should have written it on the next slide, that this method is inconsistent in function space. It just captures something in vector spaces. Are there any questions about this subtle point? No? But this is a subtle point. So even if you think you've understood everything, you'll see that it's not as simple. Okay. So yes, good. You could do that, but then you are having a problem, right? Because you could do that. In principle, you could do. Actually, the problem is much more severe than that, because in practice, even though ideally we would like functions to functions, we want to learn functions to functions. In practice, no one gives us that, right? So we always have data on discrete set of points. You could do that, that might help. But now the convolutional neural network, how do you train it, right? Means it sort of becomes that's a good point. And we will talk about that, okay? So now the question that comes up is, okay, so how, it's not like operator learning or operator approximation is something that we are doing now. If you remember, already in the last lecture, I told you the traditional numerical methods are doing exactly the same thing. At the end of the day, they were also learning operators, right? Because the solution of a PDE is an operator, solution of an ODE is an operator. So they were anyway learning that, right? So how do traditional numerical methods do this? Or do they do this? Do they learn operators, or do they learn finite dimensional representations of them? Let us spend the rest of the lecture today trying to understand what traditional numerical methods can tell us. Okay, so let's start with some traditional numerical methods. I have some blank pages because I want to explain it, write it slowly so that you get the point. Okay, let's start with the heat equation in 1D. So you have Vt equal to Vxx, right? This is the heat equation. V at 0x is equal to some V bar, for instance, of x. And V at the boundaries is 0. So this is just the heat equation. You have been given a space-time domain, which goes from 0, 1, and up in time here. So this is time, this is space, and so on. So remember, this is also something that I introduced in one of the lectures. So what is the heat equation? So what you do is you have a grid, right? There also we have grids, means. So you have a grid. And then at any point on the, so this is, I call it as V and J. So N is time. So this is time delta T. And in space, I can call it as delta X probably. And the equation is something like this. So V and J plus 1 is equal to, or minus V and J, let's write it like this, plus delta T is equal to V and J plus 1 minus 2 V and J plus V and J minus 1 by delta X squared. Right? So this was my numerical method. which implies this binary difference method, unj plus 1 is equal to 1 minus, 1 minus 2 delta t by delta x squared, bnj plus delta t by delta x squared, bnj minus 1 plus bnj plus 1, something like this. In other words, what does the numerical method do? It takes values. So what is my operator? Let me write down a few things here. What's the operator? The operator is mapping that takes v bar, which is my initial data, to v at a later time t. So let's say at the final time. It could also be the trajectory, but let's keep our life simple. And let's say that you just take the initial data, some initial data here, and you take the solution at the later time. So that's the basic idea, right? So this is going to be your operator. How does a finite difference scheme do it? So this is how it does it, right? So it's not very different from what I just told you. It starts with, now I'm running out of colors, dark green probably. So it starts with these values here. So you fix your delta x, and then you start with these values. So v bar j, and then this is a scheme. It takes you to v capital N j, right? So what is being done here is that I have a vector which is sampled on a grid, and I take it to a vector. Okay, so something very similar to what I just told you guys, that you start with a function, but you evaluate it on a grid. Okay, and then you use the physics, the underlying physics, which is given by the heat equation. And then you march forward in time to the next step, you march forward in time to the next step, you march forward in time, and you stop at some point, and this gives you a vector. Now, if you want to evaluate it as a function, you do an interpolation. Okay, so you do an interpolation. So again, start with the function, you put it down into some vectors, grid values, do some processing. This is where the physics comes in. Produce another vector and interpolate. So this seems like in a very same spirit of what we have done before, right? And it turns out that this will identically be in the same spirit. So the finite difference scheme can be written as, given a function v bar, you go to a vector. So this is some sampling. Then you process it, and then through interpolation, you go to a later function, v and t. So that's going to be the basic idea here. It is the same with finite elements. Maybe it's worth revisiting that, because all these numerical methods we are going to rewire, we are going to reconfigure to design operator learning methods. So let me just write down finite elements, but let's do it for the Poisson's equation. Rather than the heat equation, let me do it for the Poisson's equation just very quickly, so that you also learn what that is. So let me take the Poisson's equation, which is minus u double prime of x is equal to f of x on 0, 1. And then let's say that we have 0 boundary conditions. So a finite element method, some of you might know this, others might not. It's a very, very simple method. So what you do is that you start with a domain. Again, you discretize it. So divide it into points, right? And then what you do is essentially you have, you do the following. Okay, let's write it like this. You choose what are called hat functions. So these are functions which, let me draw. So this is the jth point. So hat function looks something like this. So this is phi j of x. Okay. So it takes the value 1 here, and it takes the value 0s at all the other nodes. Okay. So this is what is called a hat function. I can write down a formula, but that's not important. So you choose all these hat functions, phi j from 1 to some capital N, depending on the number of points that you have. And then the computation is the following. The steps are the following. So your input is now, so what is operator? I always forget to write the operator. Operator is going to be f, which goes to u. So f is a source term here, and it goes to your solution u, right? So input f. So what you do is that you compute, you take this, and this is nothing but f Pj of dx, 0 to 1. So think of this as a basis. Okay, it's not an orthonormal basis, but it's nevertheless a basis. So think of this as a basis. So given an input f, your source term, load vector, you produce what are called the load coefficients. So these are the values of f at each of these points. Okay, so that's the first. So the input is reduced. Again, you take a function, you reduce it on a grid. Now these are no longer grid values. Okay, so that's the difference. These are some basis coefficients. For some particular functions, this can be grid values, but in general, these are not grid values. So you have this, and then you do some processing. So let me use this number here, processing. And what is the processing? Is that given f, or given fj, you find uj. And what a uj? Uj is essentially A inverse of fj. A inverse acting on the vector fj, and A is what is called the stiffness matrix. So for those who know this, this is a very simple matrix, n cross n matrix, whose elements are given by the integral of 0 to 1 of gradient of phi, gradient of Vj, dx. Okay, so this is what is called a stiffness matrix. We invert the matrix. So this will give you the solution vector. And then in the last step, the output, because your hat functions are a basis, your output u is simply uj phi j of x, summation over j. So what is the arrangement here? Again, you start with the input, which is a function. You compute some realization, some discretization, some realization of it, which is given in terms of coefficients of a basis. You process them. This is where you use the physics, because the physics tells us that we are solving the Poisson equation. So you have this inversion of this matrix by various means, and the output, which is also given as the values of the solution at these points, you interpolate them using a basis. Okay, again, the same sort of arrangement that we have. So it seems like all numerical methods are sort of converging towards the same story, which is what I'm going to write down in a second. But is it clear? You start with the function, you do something with the function, you reduce it to finite dimensions, you process it in finite dimensions, you use the physics here, and then you reproject it back to infinite dimensions by essentially having a basis. So for instance, interpolation here could be with Lagrange polynomials, piecewise linears, whatever. This is with hat functions. And similarly with spectral methods, this is the third thing that I wanted to explain very quickly, because all of these have some machine learning analogs. That's why I mention it. Again, this is this. And now in spectral methods, my basis is provided by what are called trigonometric functions. Trigonometric functions, which in a very simple case, I can just take as sines. So in other words, the basis is provided by sine k pi x, for instance, or k2 pi x, but let's say that your sine k pi x. So now your input is reduced to the following. Fk is going to be given by my coefficients with respect to, so you have 0 to 1 of f of x sine k pi x dx. So given f, I find fk. And then there is a processing, let's say, or solution. And this is simply given by finding coefficients, uk to be fk divided by pi squared, k squared, something like this. I hope this is correct. I'm pretty sure. And then finally, the solution itself is given as u of x is simply equal to uk of sine k pi x. So when I differentiate it twice, I get back what I want. So roughly speaking, it is like this. So the same kind of a scheme. So given f, you extract finite coefficients fj. So this is your projection. And then you go processing. This is where you use the physics. And then finally, you have some output uj, which goes back to a function u by some interpolation. So this is interpolation. And here it is done with respect to the trigonometric basis, sine functions. Here it was done with respect to hat functions. Here it was done with respect to some Lagrange basis. Okay, so these are the different ways in which you can think of it. It turns out that all numerical methods can be rewritten in this abstract scheme. Okay, and this abstract scheme is what I have just done. So remember that my mapping at the end of the day, I shouldn't be running out of time. I just explained this and then we stop. So I take a mapping from a function space to a function space. This is given by G. And what do numerical methods do? Is now forget this D and P, but look at these E's here. So this here is what I call an encoding. Encoding is simply a mapping which takes an infinite dimensional object and produces a finite dimensional object at the end of it. Okay, so infinite dimensions to finite dimensions. It's an encoding that you do. So for instance, here it was point values, these were the Fourier coefficients, node values, and so on. So this is the way to think about it. Then here you do some processing. This is always at the level of finite dimensions. And this is precisely where the physics is going to be used. And finally, you have some finite dimensional representation, but you have to lift it back to infinite dimensions. So there are, this is, you can think of it as lifting, but I like to call this as reconstruction. And this is where you essentially interpolate either with polynomial basis or like hat functions, Galerkin basis, Fourier interpolation, and so on. So numerical methods, all of them can be written in this abstract form, that you start with infinite dimensions, a function, but they come back to finite dimensions, values on a grid, sort of coefficients with respect to a basis. They do some processing using the physics, using the fact that we have PDE, and they go back to infinite dimensions, right? So this is what we are also doing with the mapping with respect to the convolutional neural networks. We were trying to do something similar, and we didn't like it. Well, so what is it that numerical methods do differently, right? So there is a nuance to that, which I'll explain in the next lecture. But so numerical methods are just this, whatever I just explained in front of you. However, if you want to emulate this with neural networks, for instance, the difficulty is that we don't a priori know two things. We don't know what is going to be the processing here. In particular, we only have data. We don't necessarily know the physics, right? Just remember that at the end of the day, I have been given data and I'm going to sort of interpolate that data, right? So this is something that we don't know. And we don't know what are these encoding and these reconstruction operators. So this is somehow things that we are going to learn from the data. And by changing these objects, we get a whole variety of methods, which are what are called operator learning methods. And this is what I'm going to do from the next lecture onwards. In the next lecture, I'll have a whole slew of these methods, which are essentially based on this kind of formalism that I have introduced here. And how do they behave with respect to different grid resolutions and so on? This is a question for the next lecture. Okay, so this will be the abstract scheme that we are going to extract information from. So we are going to generalize numerical methods while remembering that we don't necessarily have the physics and we don't know what is a basis, what is a perfect basis, what is a perfect encoding, and so on. So what are the choices that we are going to make? That will be the goal of the next lecture. Okay, so I think I stop here. I could have started on one concrete example, but how much can I do in 5 minutes? Not much. So we stop here. So next week, we proceed further. Okay, good. No. So